Hello everyone, today we're going to be talking about neurophysiological mechanisms. More specifically, we're going to be discussing how a nervous cell creates an action potential, a nervous impulse in other words, how this nervous impulse is being transferred, and how is the cell during resting potential. Let's start first by discussing the first and most important concept, that is the membrane potential. What is the membrane potential? The membrane potential, or equilibrium potential, is the nervous cell's electrical difference between the electrical potential difference or electrical charge difference between the interior and exterior of the cell, on the interior being more negative and on the exterior being more positive. What determines this? Well, basically the cell is a living thing. It is a molecule. It is formed by many molecules and many atoms. Basically, this is given by the ions, and the ions are distributed in such a way in the biological systems that we've got this membrane potential, and it is maintained by other mechanisms. The ions that are governing the intracellular space are potassium ions. The ions governing the extracellular space are sodium ions. Now, potassium, you might think, how do potassium ions, which are positive, giving this? Well, basically, even though they are positive potassium ions, there are less other ions, and potassium ions themselves are about 42 milliequivalent per liter, which is quite few compared to the sodium ions, which are about 100 times more, you can see, or 150 milliequivalent per liter. But this isn't the major determinant. The major determinant is the negative anions. What do we mean by negative anions? Negative anions are negative molecules that are linked peptides, and these negative anions cannot leave the cell because they are linked to peptides. They cannot leave because these peptides cannot exit the membrane, which is liposoluble, and peptides are not liposoluble, so they cannot exit through the membrane, and they stay here, and they are the major determinants. Of membrane potential. Now, that being said, we can move on from this point to discuss what maintains this sort of ionic distribution, other than the, of course, major determinants. But this is being maintained by important mechanisms, by important structures. These structures are called the ion channels. The ion channels are of three types. And before we start classifying them, we should discuss what are the ion channels in the first place, which seems just simply right and natural to be discussed. Ion channels in general are complex molecules. These complex molecules present two parts. They present a steric external part and an intrinsic part. The ion channels that we are concerned with right now, currently, in this process of membrane potential and cellular electrical potential, are the leaky channels They are called leaky channels because they just simply allow ions to go in and out, depending on their specificity. For instance, potassium leakage channels allow potassium ions to pass through into the cell. And this happens because the potassium channels, leakage channels, have a specific structure in such a way that this structure, let's imagine that we've got a lock and key sort of compatibility. Let's say that this is the potassium ion and this is the channel. See? And then you've got another molecule, which is the sodium ion, which eventually won't pass through because there's no compatibility, and molecular weight does not provide the ability to pass through that specific leakage channels. And these are the leaky channels. How are the leakage channels important? What is their importance? Basically, leakage channels of ions allow the passage of ions into the cell, maintaining the negativity. That is, they allow potassium ions to go into the cell, and thus we've got potassium ions concentrated into the cell. Going on from this point, we can talk about the voltage gated channels. But before we go on to describe the other parts, the other two categories, we should also complete the whole image of the membrane potential maintenance, and that is the sodium potassium pumps, and these are well known. They are well known mechanism. That is, we've got sodium and potassium, 3 sodium ions being pumped out in exchange for 2 potassium ions being pumped in. Notice the difference here. 3 positive ions are leaving and 2 positive ions are going in. Now you might ask, how are the sodium ions being recovered if they are being constantly pumped out? The cell is not sitting down. I mean, you are not sitting down when you are at rest. You're actually active. The body is always active. The cells are always doing a mechanism: breathing, circulation, metabolism. The body is always active. There's no such thing as complete rest. That is death, and we're not talking about death here. So your mechanism, when there's no action potential in the resting state, resting membrane potential, this pump together with the leakage channels maintain this sort of negativity together with the major determinants, the anions. So we've got the pump 1. This is number 2 actually. Number 1 is the major determinant, the anions, the pumps, and the leakage channels. 3 mechanisms maintaining this electronegativity. We must not forget these 3 mechanisms that keep the cell during rest in its potential. Why is it important? This we'll know very, very soon, just right now. It's a very important concept. And thus, as we said, the sodium ions are being pumped out and they are being recovered by sodium leakage channels that allow sodium ions, specific for sodium ions, to go into the cell and recover the lost sodium ions. Now, that is the membrane resting potential. Now, to go back to describe the other kinds of channels that are involved in the whole electrical activity, we've got voltage gated channels. They are called voltage gated because they are opened only at certain instances. That is when there is an electrical activity. So voltage gated ions, when there is an electrical potential or electrical impulse in the neuron, let's say action potential, these channels will basically just open up, and we'll have ions going in. When the ions go in, let's say sodium ions, the cell becomes more positive. This leads to a positive intracellular charge. What does that mean? This happens in a sequence. Basically, these voltage gated channels are opened because of a generated action potential that comes from another cell. So we've got an action potential. Basically, an action potential is fired. The cell grows. The action potential, this charge is cumulative. Basically, it comes from one neuron to another neuron to another neuron to another neuron, reaching up to the peak where we get a certain positivity that opens the sodium channels and leads to a strong enough action potential that propagates from one neuron to another, leading to a muscle or to the nervous system and initiating a thought or initiating a muscular movement. Basically, it starts as small, or rather weak nervous signals, weak membrane potentials, small positivities, until they reach a sort of threshold that is about 90 or so, something around that value, about 90, positive 90, and thus an action potential was fired. And this is called depolarization. It is the state in which the cellular electrical charge shifts to generate an action potential. Well, does all of this start? It starts from the nervous system, of course. The nervous system is spontaneous. The nervous system can generate action potentials cumulatively, and then membrane potentials which then develop an action potential. And this is how an action potential is being generated. When we reach this 90, sodium channels open and it propagates as a strong action potential throughout the cell. And this is called depolarization. Let me just write it here, depolarization. Right. And at the same time that sodium channels are open, what do you think happens? We've got potassium ions opening as well. And these potassium ions, what they do is they allow potassium ions to leave the cell. Yes, potassium ions leaving the cell. That's why we put them inside in the first place, not to make the cell more positive, but rather to get the cell back into its normal positivity, its normal negativity. And thus the cell becomes negative again. And these are activated at a certain positivity, a higher positivity than that of the sodium channels. These are activated at a higher positivity than the sodium channels. Alright. And when this happens, this is called repolarization. Repolarization. Why repolarization? Because repolarization is the process of shifting back into the normal polarity of the cell. The last concept that we're going to be discussing today is the concept of hyperpolarization. What is hyperpolarization? As the cell loses more and more potassium ions going throughout and out, potassium and more potassium and more potassium and more potassium, the cell becomes more negative. And this is the mechanism used in the auditory system in order to transfer nervous potential to the central nervous system, and also it is used to lower the threshold and decrease the chances of depolarization by making the cell more negative and harder to become more positive. Another mechanism that I almost forgot to discuss is the ligand-gated channels, which open only by the binding of a specific chemical molecule.